Right now, in a laboratory somewhere out there in the world, physicists are firing single particles, just one at a time, through two tiny slits. And honestly, here is the truly mind-bending part of all this. Somehow, each of those individual particles knows whether anyone is watching it. Seriously, if no one looks, it behaves just like a wave, spreading out and magically going through both slits at exactly the same time. But the very moment someone looks, boom, it instantly collapses down into a single point, behaving exactly like a tiny bullet. Welcome to today's Explainer, where we're going to unpack a scientific mystery that literally shatters our everyday understanding of how the real world actually works.
So, does reality even exist if you aren't looking at it? Now, I know that sounds exactly like a late-night philosophical debate, or maybe the plot of some trippy sci-fi movie, but I promise you it's absolutely neither. What we're talking about today is the direct result of the most repeated, most rigorously confirmed experiment in the entire history of physics. It basically tells us that the universe you're standing in right now, the very device you're using to listen to this explainer, is fundamentally not what it appears to be.
Section 1. The Ultimate Physics Mystery. The 1801 Light Experiment. Okay, let's dive into this. To really wrap our heads around this modern puzzle, we kind of have to play historical detective for a minute. Way back in 1801, a guy named Thomas Young set out to solve a really simple debate. Is light a wave, or is it a stream of tiny particles? Fast forward a bit to the early 1900s, and the whole quantum era kicks off, completely upending classical physics. And then, right in the thick of the 20th century, scientists figure out how to do something absolutely incredible. They test this not just with a beam of light, but with solid matter, single electrons. It's fascinating to see how a simple question about light snowballed into a reality-breaking modern mystery. Let's start with Thomas Young's setup. He shines a light through two narrow slits onto a screen in the back. Now, if light is made of particles, think of them like tiny little baseballs, you would naturally expect to see two bright stripes on the wall, right? Makes sense. But what actually happens? Well, he gets a pattern of many, many stripes, alternating light and dark. In physics, we call this an interference pattern. It's exactly the same thing that happens when overlapping ripples meet in a pond. The wave crests add together to make a brighter stripe, and the troughs kind of cancel each other out to make a dark spot. So, conclusion? Case closed. Light is absolutely a wave. And for about 100 years, the scientific world accepted this as an absolute fact.
Section 2. The Quantum Twist. Firing solid matter.
But science never really stops asking questions. Fast forward to the 20th century, and physicists figure out how to manipulate and fire solid matter. Which brings us to a massive question. What happens when we fire single electrons? We aren't talking about a continuous, flowing beam of light anymore. We're talking about actual physical particles, solid matter, fired one at a time through those exact same two narrow slits. Common sense completely dictates that one electron goes through one slit, hits the screen, and leaves a single dot. Repeat that 1,000 times, and you should just get two very clean, distinct stripes, right? Well, instead, scientists got the absolute shock of a lifetime. The electron somehow interferes with itself, even when it's fired completely alone, one by one, with absolutely nothing else around to bump into. Over time, all those single, solitary dots build up to form the exact same wave-like interference pattern as the light did. Think about that. Somehow, a single electron acts like a wave, spreading out, going through both slits at once, and interfering with its own path. I mean, that is strange enough. But here is where it gets genuinely unsettling. Section 3. The Observer Effect. Watching the impossible. So here we are at the absolute climax of our scientific mystery. To finally figure out which slit the electron actually goes through, physicists just placed a detector right at the slits to watch it. That's it. Not to block the electron or mess with it physically, just to passively watch. And the difference was immediate and shocking. Unobserved, those electrons build up that complex wave pattern. But the very moment that detector is turned on, the exact second they measure which path the electron takes, the interference pattern completely vanishes. The electrons instantly start behaving like ordinary particles again, hitting the screen in two simple, clean stripes, just like little bullets. You stop watching, the wave pattern comes back. You start watching, it disappears again. Every single time.
All right, so the really crucial takeaway here is understanding what we call the observer effect. And to be clear, this isn't some measurement error, it's not a weird glitch in the lab equipment. It is literally one of the most rigorously verified results in all of physics. The simple act of recording that which path information physically changes the behavior of the particle itself. Now, I want to be incredibly clear on this point because it's often misunderstood. This does not require a conscious human mind or a physical eyeball looking at it. Any physical interaction that records the path information completely forces the electron to pick a definitive lane.
Section 4. Explaining the impossible, the wave function.
So how on earth do we even begin to make sense of this? This discovery was so profound that it literally forced us to rewrite how we view reality at its most fundamental level. To explain what's going on, physicists describe a particle's potential behavior using something called a wave function. Basically, before you measure it, the particle doesn't actually have a single definite place in the universe. It exists in this hazy cloud of probabilities. It's a mathematical description of every single possible location and state the particle could be in, all at the exact same time. It is only when you measure it that this wave function collapses, and that entire cloud of hazy possibilities violently resolves down into one definite measurable outcome.
Let's see how this ties into the really famous Copenhagen interpretation. This is essentially the mainstream way physicists understand that wave collapse we just talked about. And it is the exact reason Erwin Schrödinger imagined his very famous, and thankfully totally fictional, cat. Picture a cat sealed in a closed box with a radioactive trigger, and that trigger has a perfect 50-50 chance of going off. According to the Copenhagen interpretation, until you actually open that box to look inside, the quantum equations treat the cat as being both alive and dead simultaneously. Not just because we don't know the answer yet, but because, in a very real, strict mathematical sense, neither outcome truly exists until observation forces reality to finally resolve itself. Of course, not everyone agrees that this is the whole story. While physicists overwhelmingly agree that this quantum weirdness absolutely happens, because, well, we see it in the lab literally every day, they still passionately debate why it happens. Aside from the Copenhagen interpretation, some favor the many worlds theory. That one argues that the wave never actually collapses at all. Instead, every single possible outcome actually does happen, just branching off into separate parallel universes. Wild, right? Others prefer the pilot wave theory, suggesting particles actually do have definite positions at all times, but they're just being pushed around by a hidden, undetectable wave. Honestly, nearly a century later, the debate is still totally raging on. Section 5. Why quantum physics matters. The tech in your pocket.
Now, you might be sitting there thinking, okay, this is super weird, but what does it actually have to do with me? Well, quantum mechanics is absolutely not just some fun thought experiment locked away in university laboratories. It is by far the most precisely tested theory in the entire history of science. When physicists run the complex math on quantum mechanics, their predictions end up being accurate to about 1 part in a billion. Let that sink in. 1 part in a billion. It is astonishingly, undeniably real.
And that incredible precision brilliantly illustrates how this mind-bending abstract math directly powers our modern world. Those tiny semiconductors and chips inside the smartphone in your pocket, they literally only work because engineers understand and utilize a quantum concept called tunneling. Life-saving MRI machines in hospitals, they rely entirely on something called quantum spin. The GPS satellites that guide you to the grocery store need quantum-corrected atomic clocks just to stay accurate. Heck, even the sun itself only shines because quantum tunneling allows hydrogen nuclei to fuse together, something that classical physics says absolutely shouldn't even be possible. The weirdest theory in science is also, without a doubt, the most useful one we have ever built. So the next time you look up at the night sky, or even just glance down at the phone in your hand, I want you to remember this thought. Reality, at its foundation, is a landscape of possibilities waiting to be resolved. At the very smallest scales of our universe, nothing is entirely definite until it interacts with something else. We didn't build this strange quantum theory because it is comforting or because it makes common intuitive sense. We built it because time and time again, it is exactly what nature actually does. If this explainer made your brain itch a little bit today, congratulations, that is the exact right reaction. Honestly, it's been doing that to the smartest physicists on Earth for 100 years now. But our story doesn't end here. We are currently using this exact same quantum weirdness to build an entirely new generation of technology. So the question is, are you ready to see how these impossible particles are being used to build quantum computers? Let me know your thoughts down in the comments, and be sure to join us for our next explainer. We'll tackle exactly that. Until then, keep questioning everything.